we are going to work on what is called implicit differentiation. What would you do if I asked you to find the derivative of x squared plus y squared equals 25? What would you do? Subtract the x squared and then square root both sides. Is that what you're trying to do? And then you have y by itself to find dy dx. What about this guy? X squared plus y cubed plus y equals 2. Not going to work so well there, is it? Okay. How do these equations look different compared to the ones that we've been working with? Okay. These aren't solved for y. There's more than one y. The y has an exponent. There's lots of different things that we can point out. Okay? So these are what we call implicit equations. All right? Explicit functions are where y is explicitly written as an equation of x. So y is solved for and explicitly written as a function of x. Okay? Versus this guy right here is implicitly written as a function of x. Okay? It is not solved for y, and there's really not a way to solve for y. Okay? Some of them aren't even going to be true functions. Okay, like x squared plus y squared equals 25, that is a circle. That's technically not a function, okay? So really I should say y is implicitly an equation of x, because not all the time are we going to have functions passing the vertical line test. Okay. So how is that going to affect how we take derivatives? Okay. Let's think about this. Okay, wireless is a little slow today. Sorry about that. The derivative with respect to x of x squared. What would you tell me? Plus 2x. Okay. Now, the derivative with respect to x of y cubed. Okay. You are not wrong. Well, you are not completely wrong if you say 3y squared. However, do you notice I'm asking you to take the derivative with respect to x, but that is not x? What?
Like, we don't know x.
Right. But we are taking the derivative with respect to x. So we can still say 3y squared, but we have to apply the chain rule. All right? So since y is inside, we have to take the derivative of y with respect to x. Okay? Essentially, if you are taking the derivative with respect to x, but you have a term that has a y, then when you take its derivative, you have to multiply by dy dx. Okay? To apply the chain rule. Okay? We don't write 2x dx dx. Okay, that's 1. All right? That's redundant. We don't need to write it. However, when our variable doesn't match, we actually write it because it's not 1. Okay, it's an actual value that we potentially need to find. Okay? What happens if I give you an equation that looks like this down here and I say find the derivative? All right, this is what I'm going to have you do. Okay, the first thing is you need to differentiate on both sides, okay, with respect to x. Every single term, right side, left side, wherever it is, you need to differentiate with respect to x. Okay. Now, you might have all of your terms on one side and they equal a constant. You can have 5 terms on one side, 4 on the other. I don't know what your equation is going to look like, okay? But if there are any terms that involve a y, you're going to get some dy dx's attached to terms in your derivative. So what I'm going to have you do is anything with a dy dx, collect those together on one side, and any term that does not have a dy dx will be on the other side. On the side with all of your dy dx's, if there's more than one term with a dy dx, we'll need to factor dy dx out and divide the rest over so that we can actually solve for dy dx. All right. It's going to make more sense with an example. So go ahead and write this one down. Okay. We need to take a derivative. It's going to be implicit because we do not have an explicit function of y equals something in terms of x, okay? Be very careful. Do not forget the rules that we just got done working on, okay? So y cubed. What is the derivative of y cubed? 3y squared. But since we are taking the derivative with respect to x, and y is not x, we need to multiply it by dy dx to apply that chain rule. Plus, we need to take the derivative of xy. Well, what is xy? It is a product, which means we need to use the product rule. So the derivative of x is 1 times y plus x times the derivative of y. Well, the derivative of y is 1 dy dx. Okay? Right side of the equation, derivative of 3x. 3, and the derivative of plus 1. Okay, derivative of 1 is 0. All right? Okay, so we have some terms here. Some of them have dy dx's and some of them don't. So that second step of my process for you, everything with a dy dx needs to be together. Anything without needs to be on the other side. So I'm going to keep 3y squared dy dx and x dy dx on this left side of the equation. And then I'm going to take this 1y and subtract it over to be with the 3. Then, since we have more than one term with a dy dx, we can factor it out. So dy dx we can factor out of these two terms. Left over is 3y squared plus x. So to isolate dy dx, we need to divide that rest of it over. So our derivative dy dx is 3 minus y over 3y squared plus x. If you have an implicit equation, your derivative will more than likely be in terms of both x and y, and that is okay. It's not a problem at all. Questions about anything that we just did right there? Okay. So let's talk about this problem right here. Do you agree that xy equals 1 is the same as y equals 1 over x? Are those the same equation? Just rewritten differently, right? Okay. Well, let's talk about the difference in solving these derivatives. Okay. Let's go to the right side over here. If we were to solve for the derivative of 1 over x, how do we like to think of 1 over x? X to the negative first. So if this is x to the negative first, then when we take the derivative, we have negative 1 times x to the negative second. And most of us will just circle our answer and move on to the next one, right? Some of us may rewrite it as negative 1 over x squared and then move on to the next. Okay. Now, xy equals 1, that is written as an implicit function, right? Where we are not solved for y. That's fine. We can still find the derivative, okay? If we decide to attack this by keeping it as an implicit function, let's talk about how we would do that derivative, okay? We have x times y equals 1. Well, x times y, that is a product. So derivative of x times y plus x times the derivative of y equals, what's the derivative of 1?
0.
Okay, this might be the most difficult part about implicit differentiation. Remembering that the derivative of a constant is 0. It is so easy to want to just keep that as a 1, but please remember that the derivative of a constant is 0. Okay? So, if we want to solve for dy dx, we would have to subtract that 1y over, and then divide by that x. Well, Mrs. Homan, those don't look the same. Well, what is y? If y is the same as 1 over x, then negative y over x is the same as negative 1 over x squared. Okay? So we get to the same derivative, okay? But implicit differentiation, it took a little bit more time, didn't it? Okay? Implicit differentiation should be saved for those equations that have to be written implicitly. okay? You don't really want to have to do it unless the function calls for it, okay? So y equals 1 over x, we can write it that way, and that's a good thing, all right? We'll stick with our derivative that way, okay? Now, we are not only going to use implicit differentiation for y functions written in terms of x, okay? We could see some t's, we could see some r's, we could see some s's, we could see any variable under the sun, okay? So what I want you to keep in mind when we're doing this is that if you are differentiating with respect to x, and there is a term that is not an x, you have to use this method of the chain rule, right? You need to multiply that derivative by dy dx if it is a y. If your term has an s, ds dx. If your term is a q, dq dx. I don't care what it is, but if you are differentiating with respect to x, and you have a term that does not have an x, it is a different variable, you have to apply that chain rule when you take the derivative. Okay? In this section today, I think you're only going to see y's. However, I take that back. I'm actually not exactly sure. But as we move forward through different things that we can do with derivatives, especially in Unit 3, we're going to need to be able to apply this to any function, okay, with any variables. All right. But what you're mostly going to see us apply this to in this chapter, writing tangent line equations. So I want you to go ahead and write down this equation and then write down the coordinate that we want to find the slope of the tangent line to. Okay, so if we want a tangent line equation, what's the first thing that we need to find? I'm very sorry. We need to find the derivative, and with the derivative, we can figure out the slope of that point. All right? So let's talk about the derivative. All right? I need you to be able to recognize that that is an implicit function, and you are not going to try to solve it for y. That is not worth your time. Okay? So implicitly, we will take the derivative. All right, derivative of x squared. Okay, that's nice. Minus, here's where we need to be careful. We have xy. This is the third time we've seen it. We know that it is a product rule, right? However, we're subtracting xy, which means we need to subtract the derivative of xy. So you can either think of that as negative x times y, or you can subtract the quantity of the derivative, okay? I don't care which one works for you, but you need to keep in mind that we're subtracting and that it is a product rule. Okay, so I'm going to subtract the quantity. So I have the derivative of x times y plus x times the derivative of y, which is 1 dy dx. Then we have the derivative of y squared. CJ, what are we going to write that as? dy dx. dy dx, yep. dy dx equals, what is the derivative of 7? 0. Okay. Okay. There's probably a pretty good probability that at least one of these problems you will accidentally not take the derivative of the constant. Okay. Please be very, very careful. Okay, just be very thoughtful as you're going through these to make sure that that is a silly mistake that you try to avoid. Okay, so Now, we need everything with dy dx on one side, everything without dy dx on the other side. So, we have negative x dy dx if we put that subtraction through, and we have 2y dy dx. And then what I'm going to do is I'm going to subtract 2x and add 1y over to the other side. Okay. These two terms have dy dx, so we can factor it out. Okay. Now, we need to divide this over. Now, our algebra skills are pretty good. I am totally fine with you writing negative 2x plus y divided by negative x plus 2y. Okay? I also realize that this could bother some of you, and it is totally fine if you want to write it as y minus 2x divided by 2y minus x. I know some of you are going to want to do that. I don't really care how you write it as long as it's equivalent. Okay? Also keep in mind that if you decide to put your dy dx's on the opposite side of mine, then your equation could look different. Okay? If you would have put your dy dx's on the right side, then your equation could have been negative y plus 2x over negative 2y plus x. Okay? Those are the same thing. They're opposite in the numerator, opposite in the denominator, which means they're still the same because you have negative 1 over negative 1. Okay? So keep that in mind when we're looking at like answer keys and that kind of thing. Okay? Now, we found our derivative. That's awesome, but that's not the only thing we need to do. Okay? We want the equation of the tangent line. What was our coordinate? Negative 1, 2. So what we need to do, and here's some notation for you, we need to take our derivative and we need to evaluate it at the coordinate, negative 1, 2, you said? Okay, so remember that big slash bar means evaluate. Do you use that in science class? No. So dy dx evaluated at negative 1, 2. All right? So we have 2 minus 2 times 2 minus negative 1. What is our slope? I think I heard 2 people say 4/5. Nobody disagrees. We'll move forward with that. So our tangent line equation would be y minus 2 equals 4/5 times x minus negative 1. What do you think? Okay. I want to do one more example that involves trig. Okay. Going back to the quiz yesterday, when I mentioned there are some of you that still don't have your rules down, you need to figure those out this week. I am adding more rules to your list Wednesday and Thursday, which means you're probably going to have another derivative quiz, pop quiz sometime next week. And then again, and then again. Okay? It's going to feel a little bit like the unit circle where I just keep putting it in front of you to make sure you know what you're doing. Okay? You need to know these rules. Okay? All right, go ahead and write this one down. Okay, so first of all, I need you to notice that this is an implicit function because we have y in there, and we're not going to solve for y. No. So we need to keep it like this, but since y is inside of our function with everything else, it is written implicitly. Now, 2 sine x cosine y. What is that? It is a product, which means we need to use the product rule, okay? So those are the two functions we are multiplying together. Joe.
Can't we take the 2 out to get rid of the 2 and make it sin x cosine y?
Okay, Joe asked, can we divide both sides by 2 and then take the derivative? Would that be legal? It would be legal. Okay, you're going to get to the same place. So, Joe, how about I keep it in for now, and then we'll see at the end how, why it would be okay to divide it over. Okay? But that is perfectly fine. So let's keep it in, and then we'll look at the answer when we get there. So, derivative of the first. What is the derivative of 2 sine x? 2 cosine x. And then we're going to multiply by our second function. Plus the first function, 2 sine x, times the derivative of cosine y. So what's the derivative of cosine, first of all? So negative sine y, but since y is inside, dy dx. And the derivative of 4 is? Okay. So we have one term with dy dx. I'm going to go ahead and rewrite it as negative 2 sine x sine y dy dx. Okay, that's this term right here. We cannot combine those signs to be together because there are different angles, x, y, they're different. And then what I'm going to do is I'm going to subtract this term over because there is not a dy dx. So negative 2 cosine x cosine y. Okay, so to get dy dx by itself, we would have to divide that over. So you can see how those 2's are going to end up canceling out, which is why it would not be a big deal to divide that 2 over and just take care of it before the derivative. 6 one way, half a dozen the other, right? It's not going to, it's going to take time, but it's just time you don't have to take here. All right? Now, if you left your answer like that, not going to complain. However, if this were like a multiple choice question, what is cosine of x over sine of x? Cotangent of x. And cosine of y over sine of y. And so you're probably going to see them simplify it to this. Okay, in the event that I might not be here tomorrow, which I'm hoping that I will be, but sometimes life happens. I want to just give you kind of a pre-warning about something here. So I'm going to go back. I'll go back to this one. Sure. I'm going to go back to this one. Sorry. Changing my mind. All right. So I wanted to go back to this derivative right here. Like, let's pretend that we didn't find the tangent line. We stopped at the derivative. If I asked you to find a horizontal, like a coordinate where the tangent line was horizontal, what do you do with your derivative? Set it equal to 0. And if we have a fraction, that really just means your numerator is 0, right? Well, what if I ask you for a coordinate where the tangent line is vertical? That means our slope would be what? Undefined. So if we have a fraction,
That means the denominator equals 0.
that means the denominator equals 0. Okay, so vertical tangent line means your slope is undefined. So in your derivative, that would mean your denominator of your derivative would need to be 0. Okay, now, maybe I'm here tomorrow and I just gave you a really big hint for what we're going to do on a free response problem, but if I'm not here, then there's your hint. Okay. So let me go ahead and stop this here.